Okay, let's move on to part 2 of section 3.9, which is on the concept called differentials, which is what we are going to be working on for the next couple of days in this unit, actually for this unit. So what we just did was we did a little prep work with the tangent lines, finding the tangent lines, doing some approximations using the tangent line. So now we're going to take that to the next level and talk about actually what the tangent line does, and then comparing a little bit of this delta y means the change in y, and dy is your differential of y. And so we'll explain what that means and then what we will be computing today. So just keep in mind, this is all pre-work for our differential unit. So we are going to use these methods that we're working with in these last two sections in order to apply them. So do some application problems moving forward with the rest of our unit. Okay, so let's just dive into this, and we're going to take a look at what they're going to ask when it means by compare change in y and dy. So I just want to give you a little bit of background information. I'm not going to go through where the proof of this formula and where it comes from. We can talk about this more in class. But change in y, if you remember the slope, right? The slope is actually calculating a change in y over change in x. That is the formula for slope. It is rise over run. And so really what a differential is doing is when we find the derivative, right? Because the differential is basically a method where we found the derivative. We did this to find the tangent line. So it's a method, we found the derivative, and then we found the slope, right? And the slope is a rate of change. And so that's what we're going to be doing here is we're going to use this method. We're going to compute the derivative and find the rate of change, which basically is the slope, and then compare it to the actual function and then to the derivative. Okay, in addition, differentials are basically we're studying the rate at which this function is changing. Okay, so how is this function changing is basically what we're going to be doing and what we will be doing in the rest of this unit. So let's first take a look at a question and see what they're going to ask us, and then talk through and work through a problem. Okay, so question number 1, example number 1, we are going to let y equal 2x squared. Okay, and then we are going to, our first question, so we're going to have 2 parts to this. So we'll say that this is part A. So part A is we are going to find delta y when x equals 2 and change in x, or delta x, equals 0.3. Okay, so let's talk through how we solve this, what we have to do, and then explain like what does this actually mean. So we're going to be using this formula in order to solve this, and the change in y, or the delta y formula. Again, this is coming from, again, I'm not going to go through exactly the point of this or where it is derived from, the proof. We can talk about that in class. But we are going to be finding the change in y, which remember is basically how is the function changing, or how is the rate of change of the function at a particular value. So how fast or slow is this changing? So the change in y is equal to the function at c plus change of x, or delta x, minus the function at c. And if you remember from our last lesson, c is actually your x value. C is the function value. So c is actually your function value at x. So that's this right here. This is going to be your c. And then our change in x is 0.3. So that means that our function is changing in the positive direction, 0.3. If it was negative, then it would be changing in the negative direction. So this is a positive changing function, and the rate of change is 0.3. So that's basically just going in right here. That's pretty easy to identify. Okay, so what we're doing here, just so you understand, that the change in y is just representing when the function the rate of change along the function. Okay, so I'm going to say that again. I will put that in text here. So delta y equals the change along the function. Okay, and then in a second, you'll see the other change we're going to talk about. So we're just going to see the rate of change of y. We know the rate of change of x and it's changing at 0.3, but we want to see when x is 2, how is y changing? And again, this is in respect to the original function. So all we're going to do is plug these numbers in. Okay, so let's do a plug in here. So I know that, okay, change in y. I need to find my c, which is 2. So my function of 2 plus my change in x, which is 0.3. And then subtract it from my function at c, which is 2. Okay, so basically what you're doing is you're going to plug in, you're going to go and plug into 2x squared, that function at 2.3, and then subtract that value from the function at 2. Okay, so again, we are checking this function right here. Okay, and we're plugging in 2.3 for that function, and we're plugging in 2 for that function. So I'll give you a second if you want to plug it in, check my math. So when you plug in 2.3, you should get about 10.58 approximately. The function at just 2, I got 8. So if you subtract those, you would get 2.58. So that represents the change in the function. So the change in y, the rate of change of y, when the function is x equals 2, and you know that your rate of change of x is 3. Okay, so here is our change of y. And again, this is along the function, the change along the function. Okay, now part B is now we're going to compare this to the change along the tangent line, or the rate of change, not just the tangent line, but the rate of change of your slope, okay, in which we find the slope when we do the derivative. Okay, so let's go on to part 2. So again, we're going to remember that our function is 2x squared, y equals 2x squared. In part B, type this in here. Okay, part B, we are finding the dy now when x equals 2 and change of x, or sorry, and dx equals 0.3. So you can see here that nothing has really changed except for our notation. So we still have an x of 2. We still have, well, our dx, which was change of x, is 0.3. So we still have the same numbers. We have a different notation now. We've changed from that delta, the triangle, to dy dx. And this is because dy represents, let me type this in here for you. dy represents not the change along the function, but the change along the tangent line now. So dy equals the change along the tangent line. So not of the actual original function, but how is the rate of change happening along the actual tangent line to the graph. So this time, we're not going to be plugging this information into the original function. We're going to be plugging the information into the derivative of the function. So the first thing we want to do is actually find dy, because remember, when we take the derivative, it's actually dy of dx. So this is what it would look like. So we take the derivative of this, so dy is the derivative of this, equals, or dy dx is the same thing, equals 4x. And then, right, we can multiply this dx over, so dy, the derivative of y, equals 4x dx. All right, not too concerned about the dx. This is really what we want right here, is this 4x. Okay, keep this dx right here. All right, so in order to find dy, this is the formula that we are going to use. We do need that dx in there. We need to multiply that dx over. And this should look familiar because this is the integral notation, right? Okay, so to find dy, okay, what we're going to do is we're going to plug it into this derivative formula that we just calculated. So dy equals 4 times x, which is 4 times 2 times 0.3. Okay, or in other words, what you are doing is you are taking the derivative value. So basically you're doing the derivative of x, or the value of the derivative of x times dx. So that is another formula right here, like the general formula that you would use is right here. So this means you take the derivative of the function, the value at x, which we're doing right now, times dx, which is the change in x along the tangent line. So all we have to do is just multiply these all together, because that's easy enough for our derivative. And we end up with 2.4. Okay, so just to compare, on the previous page, we found the change in, so this, remember the same numbers, they were the same numbers. When we used it to compare the change along the function, we got 2.58. When we compared the change along the tangent line, we got 2.4. Okay, so there is a change there in about, what is that, 0.14. So so there's, remember that this is another way we're doing approximations, just like we did with the tangent line. It's just another way to approximate how close can we use a tangent line versus our regular function. And so we can see how close they are in value, whether we use the derivative method or we use the regular method of just plugging it into the function. Okay, let's take a look at one more example so you can see what this looks like. I'm going to try to put it all on one page for you this time so we can see, just be able to compare it. Okay, so example number 2, we are going to let y equal x to the third minus 2x. Okay, and part A is to find change in y when x equals 3 and change in x equals 0.1. Okay, so remember, part A, we're trying to find the change along the function. The deltas means the change along the function. So we're just gonna use the original equation. Okay, so first thing is, let's go back to our formula that we had. So it was the change in y equals, and then we had f, so the function at c plus change in x, or delta x, minus the function at c. Okay, so all we're going to do is plug in our information and figure out what is the change in y with this information. So change in y, remember that c represents your x, this is your c. So it'll be the function at 3 plus the change in x, which is 0.1, minus the function at 3. Okay, so all this is a little bit of plugging and chugging. So we need to evaluate this function up here at the value of 3.1 and at 3. Okay, so evaluate the function at 3.1 and subtract it from the value of the function at 3. Okay, and you should get the value of the function at 3.1. I got, well, together, when you just go ahead and subtract them, I ended up getting 2.5. So approximately 2.591-ish. Okay, you can check my math on that. So something around that, maybe 2.6, or sorry, yeah, 2.6. Okay, so there is our change in y. All right, now let's go to our part B, which is going to be find dy when x equals 3 and dx equals 0.1. Okay, so again, same thing, almost the same thing, but the same numbers, right? So we still have x, and this time, remember, this change in y, change in x represents the change along the function. Dy dx is the change along the tangent line. So now we're going to compare them and see how close this approximation is using the tangent line, the rate of change is compared to the rate of change of using just the function. Okay, so the formula here, which I will be more specific, the formula here. So to find dy, we do the derivative of the function. So it'll be the derivative of the function at c times dx. okay, which is basically derivative of the function at x, right? Okay, so we have to do the derivative of x to the third minus 2x. So the dy dx, which is basically just dy, right? Because we're going to multiply that dx over. And then the derivative would be 3x squared minus 2. And then we move this over times dx. Okay, so now all we're going to do is plug in the 3 for x squared. So it'll be 3 times 3 squared minus 2. And then you have to get that answer and then multiply it by 0.1. Okay, so get that answer, multiply it by 0.1, because you don't want to, order of operations, the 2 might multiply by the 0.1 first. You need to get an answer for this value of the function at 3 first, then multiply it times dx. Okay, and when you do that, you should get approximately 2.5. Okay, so again, you can see here is you're close. You're about 0.9 away from the actual function to the tangent line, the rate of change. Okay, so again, differentials, we're going to be getting into this more with some word problems, but what are they? They are studying the rate of change. They're studying the rate of change of our function, and we're using the tangent line to help us. Remember, the tangent line, we find the derivative, we find the slope, and then we're able to find the rate of change at a specific point along the graph, and we use the tangent lines to help us. Okay, here are your practice problems. They're out of the book this time. So you're going to go to page 236. Okay, there's only 4 of them. So page 236, and you're going to do numbers 7 through 10. And you're going to do the method that we just did. So in the directions, it says to basically compare, well, it says use the following to evaluate and compare the change in y and dy. So you're going to do exactly what we just did, find delta y and dy. Let me know if there's any questions, and good luck.